So we've previously been introduced to the concept of capacitors. Now let's look at how we can store charge on them. So the way to store charge on a capacitor is to connect it to a power supply. And this circuit symbol here is what is your capacitor. Now we know that electrons get released from the negative terminal of the battery and flow around the circuit. Now what happens is these electrons then get accumulated on this plate of the capacitor. Now due to repulsive forces, since we know that this plate here is a metal plate, and we know that a property of metals is that they contain delocalized electrons, the same number of electrons that have been accumulated on plate B here will get released from plate A. And then you can see that a current will then flow in a circuit. Now a key point to note is that the number of electrons accumulated on plate B is equal to the number of electrons released from plate A. Instead of released, you could also say repelled. Now you may notice that as more and more electrons get accumulated on plate B here, plate B becomes more and more negative. So what does that mean to oncoming electrons? Well, because these are both like charges, these oncoming electrons will also feel a repulsive force. So what this means is, as electrons get accumulated on plate B, the rate of accumulation will decrease due to the repulsive force on oncoming electrons. So in other words, as more and more electrons get accumulated on plate B, it becomes more difficult for oncoming electrons to get accumulated as well. And what also happens is, as the rate at which electrons get accumulated decreases, the rate at which electrons are released from plate A reduces as well. And this one here is plate A. So what does this mean graphically? Well, let's look at how the charge varies with time. Well, we know at the start there's a much quicker rate of accumulation, and as time goes on, the rate at which electrons get accumulated decreases. So what you end up is a graph that looks something like this, where in this section you have a steeper gradient as there is less repulsive force. So therefore you have more accumulation. And here you have a more shallow gradient as there's more repulsive force, as more electrons are on the plate, so they exert a stronger force on oncoming electrons. And at this section here, you have no more accumulation. So eventually no more electrons will get accumulated on the plate. And remember that we said that Q is equal to CV, where C is a constant. So therefore, your voltage versus time graph will have the exact same shape. Now we saw that as time goes on, the rate at which electrons are released from the positive plate also decreases. And what that means for the current is that the current initially starts very high, but then decreases to zero. Now we know that current is equal to the charge over time, but for a bit more complex situations like this, the current is actually given by dq by dt. So in order to get the current graph, all you have to do is actually differentiate the charge graph. In other words, this current graph is the gradient of the charge versus time graph. But you don't actually need to know about current is equal to dq by dt for your exam. Now you need to be aware of some equations for the charge and voltages on capacitors in a charging circuit. Now the equations for charge and voltage are basically identical, and they are of this form here. But the only difference is one is in terms of V and V naught, and the other one is in terms of Q and Q naught. Q and V are respectively your charge or voltage at a specific time. Q naught and V naught are actually your final charge or voltage readings. So that means if you were to charge up the capacitor and let it go until no more electrons are accumulated, what is the final charge or voltage reading on that capacitor? T represents the time from when charging starts. and R is the resistance of the circuit, and C is your capacitance of your capacitor. Now, in the drawings I've drawn, I haven't included a resistor for simplicity, but if you did not include a resistor in your capacitor circuit, the capacitor basically charges instantaneously. Now, for current, however, in a charging circuit, as I said, you need to differentiate the charge equation, which you probably don't need to do, but if you know how to do it, you would get that the current is equal to I naught e to the minus t over RC. So all these equations have very, very similar forms. Now, this RC value in the equation is known as a time constant, which is represented by this tau letter here. And RC actually has a unit of seconds. And what your time constant is the time taken for the capacitor to charge to 63% of its final value. So either 63% of its final voltage or 63% of its final charge. So what that looks like is, let's say I was charging my capacitor and its final value was 100 volts. Well, after one time constant, it would have charged to 63 volts. And we can approximate and say that after 5 time constants, it reaches its final value. Now, the best piece of advice I can give you after watching that video is to go off and practice on past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.